Oh, is that all we need for that? Okay. Yeah, that's fine. It's just going to launch Helldivers when I log in here. I have the website somewhere. I'll do this. Let's go here, and I think it's F11.
It's robotics page.
Oh, okay. Good? We just go wired, all else fails? Or does it need to be?
It's working right.
So this is prompting for a meet. Oh, it's not bad. There's a pop-up. I wonder if I have to. Okay, let's hop out of that for a second. And then, oh.
No, you shouldn't have to do that.
Oh, okay.
There we go.
Yeah? All right. Kablam. Yeah, yeah. Cool beans. Well, don't we lead with our maze?
What's that?
He's the opening speaker, I thought.
Our maze?
Yeah, yeah.
Oh, well, okay. Sorry. Gotta hook you up, luckily.
Hey, Tyler, is anyone from your team going to be at the Robotics Summit coming up at the beginning of May out in Boston?
Yeah, there'll be a couple of us.
Oh, you guys will be out there? All right,
Yeah.
I'll see you guys out there.
Yeah, that's Wednesday. So, I'll be at on a meet.
Oh, okay, okay.
Yeah, I mean, it's about a 10-minute walk from our office, the robotics
Oh,
office.
nice.
Yeah, so it's right down the street.
Okay, okay. Yeah, I'll say hi to the guys then. I just had the relay. I don't know if we have any format or structure in mind, but I realized that I'm guessing he'll talk about OMIC, but I'll need to give an introduction to either myself and maybe why we do these projects before kicking off.
100%.
Yeah.
We'll figure it out.
Gotta speak up. I'll turn you on. Okay. You're good, go. Okay.
We can get started there. Yes, 9 o'clock. I just want to thank you all for coming out. My name is John. I'm the Director of Marketing here at OMIC R&D. I've asked our Head of Research, Ramesh Natterwala, to give a bit of a background of who we are and what we do. Once Ramesh is able to give that background, we'll hand it off to Jordan to talk specifically about this robotic cell project, the future of Cobotix. After that, we'll be handing it off to Tyler Bouchard to talk more about Flexxbotics. We'll have a brief break, and then we'll be handing it off to an individual who will be calling in, Tyler from Flexxbotics, to talk a little bit more about this project, I believe. After the presentations, we'll go do a tour of the Additive Center, the Subtractive Center, and then we'll see the robotics cell in action. So with that, I'm going to hand it off to Ramesh to talk a little bit about OMIC R&D.
Hey, good morning, everybody. So my name is Ramesh Natterwala. I'm the Director of Research at OMIC. Just to tell you a little bit about who we are at a high level and what we do, and you'll get a better feel for it with the tour and some of the things that Jordan's going to talk about in the demos. But the big thing I'd like for you all to focus in on or walk away with is our differentiations, because just about every company out there, yourself included, we have some tech center or research entity or department. And certainly the government has many tech centers and research centers, national ones, so the universities have them. So how are we different and how do we stand out? And so that's what I really want to tell the story about. So first one is we're an applied research center. So how many of you all are familiar with this thing called applied research? Some had not. So that's a big thing for us. So I jokingly say that if our research ended up only in conferences and published papers in libraries, we haven't done our jobs at all. So applied research is where the research must find a home in someone's production environments. So then everything with that focus revolves around that focus. We have essentially 4 focus areas, but we often grow from them. We have machining, we call that subtractive. Additive manufacturing, which is the building you're in. Subtractive is the other building. We have robotics. Materials and sciences are rolled into either additive and or subtractive, because that's the kind of research that members have asked for. And now we're even exploring inspections, because we've gotten into several projects that need that focus. So we grow as the asks come from the industry. So we are a membership-based organization. However, we also do research projects quite a bit for non-members. There's 2 types of projects we do. One is called a general project, and the other is specific. At a very high level, general projects are exactly as the name says. They serve the general needs of the industry. So our memberships come together. We annually do a road mapping event, and from that we select about anywhere between 6 to 10 projects, cumulatively worth in the range of about $1 million. And we give that completely back to our membership so that they can enhance their productivity. They're usually proofs of some difficult concepts, like vision systems in manufacturing, or based on what their needs, or trying to figure out machining of additively made components. So again, it's an ask from the industry. The other type of projects we do are called specific projects, and they are specifically for your company needs. So and we protect the heck out of your IP, but we return it all back to you. So that's another big differentiation. I always want to say, I'm actually very proud of it, is we don't want any stake in your IP in the current model. Here's why: because we found that we can waste a lot of time talking IP between attorneys before any IP is even invented. So we protect your IP if you were to do a specific project with us, and we return the solution back to you. In doing so, we've been able to take on and solve a lot of industry problems, and get on with it and do more projects, and hopefully through those solutions the industry speaks well of us. That business model has actually worked really well, and so that's another piece of our differentiation. And then the last one I'll talk about is our but actually should be the first one on my list, is the people. As you meet our team, you'll find a significant differentiation as compared to folks that might be in your factory floors and so on. Simple things, all our engineers come from really production-based environments and have that core. It doesn't matter where you were rooted from, you will run your own machine, so we don't have the differentiation between operator communities and researcher communities, and it goes both ways, so we're bridging those gaps. And lastly, we intend to teach the solutions of research, so we don't do the classical classroom teaching, but we help. Research always feels incomplete unless you teach the customer the pros and cons and the best practices you learn from that. So that's a big part of our knowledge transfer, and so we're really empowering that this year. That's a Reader's Digest version, right? So can I answer any questions for you folks? It gets really boring if you guys are going to be quiet through the day, so I strongly recommend you all chat. All right. Have a great day. Thank you for coming.
Thank you very much.
Got it. Easy there. All right, to make sure this works. Oh, maybe not. I think the clicker died. I mean, yeah, I can use it here. I was just going to walk over there so I'm not hidden behind here, but that's all good. Okay, so yeah, thanks for coming everyone today. My name's Jordan Meter. I'm the robot researcher here at OMIC R&D. A little bit about myself. Really passionate about robots. Loosely based my college curriculum on Tony Stark and pursued multiple engineering degrees at one time. The whole idea was wanted to be able to design it, fab it, wire it, build the circuits, everything. And then the ship just continued to get crazy at the point that I was at Oregon State University. And when the robot program was launching, the nuclear disaster in Fukushima happened, and I just happened to randomly join a lab because I thought robot hands were cool. And then that's when DARPA reached out and they're like, we need all robot hand specialists to help design the prototype for Boston Dynamics to go shut off the reactors. And that led down a wild college experience. And now I am here doing manufacturing research. So I just want to acknowledge everyone that was really helpful to making this project a success. So we worked with Olympus Controls out in Tualatin. They were the ones that provided the aluminum extrusion, the robot hardware. When we go out to the cell, you'll see a UR20 robot arm. Then Flexxbotics, obviously, is why you're here today, for all of the software, CNC integration, and the solutions that made this thing really slick and streamlined. And then lastly, one of our member companies, who is how we got the Doosan CNC, which we integrated with this project. So just a quick rundown of the order of things we're going to do. I'm just going to introduce the project. I'll describe at a high level the equipment used, and you'll see some charts giving kind of the specifications of the equipment. Then I'll break down the project tasks, the advantages to the robot cell, conclusion, and then the next steps, which kind of like what would be the next phase if this project were to continue. So kicking off this project, it was basically, for those of you that are not familiar with cobots or collaborative robots, so that is those are the arms that are able to sense a collision. One, they're able to stop in real time, but two, the extra step that comes with collaborative robots is they don't just stop, but they actually back off by a predetermined amount. That way, if they ever pin an individual or an object, they automatically release that, so there's no tension there. So this project was to explore the coexistence between the human operator and the robot arm existing in a, basically in this case, shoulder to shoulder. And then what this was supposed to do is, because they were coexisting, it was basically that they would both be accomplishing tasks while in the same area, but not purposely to not get in each other's way, so timing the tasks between the two. And then once the operator steps out of that zone, the main objective of this robot was to tend, basically replacing stock or parts within the CNC lathe. And I'll get into more later, but this was identified early on as a need not to do lights out manufacturing, but how do we remove repetitive strains, because some of the stock being loaded into the lathe was requiring some of the operators to extend both their backs and their arms, and so there was issues with loading of the rotator cuff or repetitive strains. So for the CNC lathe used, we had the Doosan TT 2500. This is the one you'll see out in the shop floor in Building 1. Just some quick stats thrown up on the left there, but this is the machine that we were integrating with. And then, as I mentioned earlier with the acknowledgements, so Ellison Technologies is the distributor for this equipment, and that's how we are tied in with them. So next on here, so then this is one of the equipment pieces provided by Olympus Controls out of Tualatin. So this is the Universal Robots 20 kilogram model collaborative arm. It works quite similarly to an industrial arm, but it has a combination of absolute and incremental encoders that allow it to know its position. It can detect with both force sensing at the end of the arm and with basically detecting current rush in motors, can detect a collision, and then, as I said, will not just stop, but back off, removing any pinch points. For those, we can go into way more details. I'm very excited about all of robotics. I can ramble on about the features once we get out into the shop floor. If you haven't programmed this style before, it's much more intuitive. We host a lot of events on site. One is a manufacturing day where we bus in like 500 to 800 high schoolers that are interested in manufacturing. And what I did last summer was I basically just took anyone that was interested, showed them the arm. The first demo I ran was, hey, step in the way, I'm gonna make this hit you. And they would see that it would just knock them, come back. But the other part was, hey, do you want to learn how to program this? Because unlike old school robots, this is basically moving a stylus in space. You can just quickly touch, grab, grab. And so within 5 minutes, I had these students just moving the robot. It's very intuitive, very low level entry. I like collaborative robots for that reason a lot. But anyway, so 20 stands for 20 kilogram, sets the payload for this arm. And that's one of the first things that was identified is in the demo you'll see today, we're not using a 40-pound part. But it was the customer had basically requested that something that could feature 10 to maybe upwards of 40 pounds, and that was the issue where a lot of their operators at the time were of a smaller stature, and so if they're stepping on a step ladder, completely extended reach, trying to load something that's up to 40 pounds, they were seeing a lot of strains on their production floor. Okay, the end of arm tooling, a robot gripper. So this is produced by On Robot. This was also provided through Olympus Controls. It is a cylindrical gripper. Those 3 fingers, and we'll see it on the floor when it comes by. So those actually spin concentrically. So you provided a cylinder, and then it will spin down. Now, one of the nice features about that is if the cylinder is off center, it'll just pull it back to center. And then one of the added features is you can actually spin those fingers all the way in, and then say you had a large outer diameter you wanted to grab, you could actually just reverse it back out and then grab from the inner diameter of a part. Just some metrics of what this was able to handle. This one advertises, where did you go? About, what is that, 22 pounds is what I'm looking at, but it's able to sense different positions. So you can actually put this in a predetermined, you can put it in a predetermined grip set, but the example you'll see today, the feature I use is flexible, so it doesn't even know what diameter it is. It just senses when it makes a collision, and then it'll actually mechanically lock those fingers in place. So if you de-energize, there's no risk of dropping the payload. Once it goes in, it breaks, it's rigid. Okay, and then, so this is the software we use today. This is software and hardware. This is with Flexxbotics. So if any of you are familiar with robot integration at all, either you've maybe worked with industrial robots or let's say systems that are not Flexxbotics. I was an automation integrator for a couple years in the aerospace industry, traveled around, would fix heavily broken systems. It's not the cleanest process. There's a procedure, there's a way, there's an art to make it right. But when that CNC or that control panel in PLC, when that was originally produced, it wasn't really intending for someone else to drill a hole in it and then start, splicing cables. And so if the integration is coming much later on, it usually involves either cutting a panel, you then have to start splicing I/O cables that the PLC was never intended for, and you result with either one or two large umbilicals coming out of the back of the machine. That was something that this customer for this project also identified early on, is that, hey, we don't want large, ugly umbilicals coming out laying across the floor. We don't want the tripping hazard. We also don't know how long we want to keep this particular CNC automated. So we prefer a solution that you could quickly implement, but then with minor interference to the machine, just disassemble and move on to another machine. Well, with the Flexxbotics system, we got that with a single Ethernet connection. So I cannot overemphasize the simplicity and speed in terms of just, oh, cool, you have an Ethernet IP card on your CNC controller. We didn't even have to go to the back of the machine. We just saw an available Ethernet port when the Flexxbotics team came out here. I'm like, oh, I bet we could just plug in here right next to the operator and immediately get control. And that's what happened. So it is, compared to doing the laborious task I've done in the past, this is immensely more streamlined.
Is this developed by OMIC or by the Flexxbotics?
Say that again?
Is this Ethernet connection developed by your OMIC or is developed by the company like Flex?
Oh, it's Flex. It's Flex. So it's basically, there was a pre-existing, so for those that are like in the computer hardware space, you'd usually call it like a NIC, a network interface card. So there was a pre-existing FANUC network interface card within the Doosan CNC, and then Flexxbotics produced, can I get my cursor moving here? Yeah, let's do this. So this, it says Flexxbotics on, so this was like their main, oh, sorry about that. That's their main control box. And then where you see, if I can get the cursor without changing the slides on me. So then right here where it says machine. So we basically just plugged in straight from the operator's control panel into that machine port, and it was immediately able to see the status of the PLC and start tapping into I/O. And then all these ports that you see down here, like the green, that's so you can tie out to your own equipment. So that's expansion. That's not needed to go back to the machine. Literally just the single Ethernet going from the CNC into that machine Ethernet port there on the black box. And so single Ethernet connection, it was really quick to set up. And then going back to the green ports, so easy access of I/O, just having direct connections where you can just immediately start calling out like, okay, now if I just want to be able to flag or read out what, is there a cycle start? Is the door open or closed? For us, we had, but it's already labeled in there as well. So you have vice, chuck, whatnot. Then as we break down into the more advanced features, and then you can kind of see like there's a network topology, the top image, and to the right is more like data analysis and heuristics. So this is where the software goes into a much more advanced level. So in my case, they were able to pull information. Had we been running jobs on this machine, you would be able to see historical data on how many parts it's run through, what amount of time did it take. It's constantly monitoring for errors. So if there's a crash, if something was out of spec, if we do not have a probe in our CNC, but you could do in-machine inspection and then update the data charts as such. In my case, what I had not seen before that I really, really liked was the remote support that was offered. So in cases where I'm like, okay, I'm not sure where this chart is, I need help getting this set up. Their team, kind of if you're going off like the top image, they were immediately able to remote in and then see the status of the automation cell. But further better was, oh no, I was messing around with the UR and I didn't crash the UR, but I definitely screwed with their OS in a way they didn't expect. And so I caused a software crash. So the pendant was just frozen out. Well, the pendant's just running an OS on top of an OS. And so when I contacted Flex, like, oh yeah, that's an easy fix, no problem. And then they remoted into the frozen pendant, pulled the error logs, was able to diagnose how it crashed, helped me reset the robot. And then furthermore, if I was less familiar with robotics, probably one of the just really nice like teaching or hand-holding features is they can just make a mouse cursor appear on the pendant. So if you're just completely like, I don't know what button to hit, they'll just point at it for you. They'll be like, do this, do this, do this. Now from a safety standpoint, they're not gonna control the robot remotely for you, But being able to call in and just have a person who's never touched it before and then just have it just appear on the pendant of like, oh yeah, hit this thing that I'm pointing at or flashing. That is an insane level of support for someone who doesn't know what they're doing on the pendant. Just being step-by-step guided through the process.
What OS is usually in?
So this one I think is, so the UR, because that goes back to their operating system. So that's Polyscope. I believe Polyscope is running on top of Linux. And then I believe that, Tyler, correct me if I'm wrong, you guys might also be running Linux?
Yeah, it runs on Linux, and then we have our own proprietary Flexxbotics that does all the communication.
So usually in my experience, but I'm not the one who programmed the pendant, if the pendant has frozen out, that is usually that Polyscope software that's on top of Linux, but Linux is still running in the background. That is also a case where if you do run into an error, you can power cycle to kind of get out of it. I purposely did not do that, and if you run into a similar case, because you have a good likelihood that those error files or whatever position that you need to diagnose is stored in temporary memory. So if you cycle it, you just wipe everything needed, which was the other reason why before just trying it on my own, called it Flexxbotics. Flexxbotics went into there, and they're like, cool, you didn't wipe anything. We can actually diagnose this, and then moved on from there.
Polyscope is the name of the software.
Yeah.
Can we take picture of the slide in the phone?
Yeah, there's nothing proprietary.
If he doesn't use the microphone, can you repeat the question?
Oh, yes, fair enough. The question was, well, the first one was if Polyscope was the OS for the pendant, and then followed by if pictures are allowed for this presentation. Nothing proprietary exists in these slides, this version of this PowerPoint. So if anyone sees information they want to gather, and then John, I don't know what our policy is for just handing out the slides. But again, there's nothing proprietary in this one, or at least I'm not revealing. I'm just more so, these are the products, this is the process we went through. So moving on. This is one of the safety, it's technically only safety component outside of the universal robot arm. So in an industrial sense, if you've seen that, car manufacturing lines are a great example. You have giant robots moving heavy parts, you usually have to lock it out with cages. So this goes back to collaborative arms with their sensing features do not require to be caged out. Now you still want some sort of sensing so the robot is aware of what's going on around it. You don't want to just go, well, the robot can detect collisions, so we'll just let it operate until it hits a person. Like, well, you want to give it some sort of insight. So in this case, we used, the manufacturer is SICK, and this is their nanoscan. I think I have another photo, but I'll toggle back real quick. Yeah. So I have a photo revealing scale. This thing's pretty small. That's basically a 2D light zone scanner. We have 2 of them positioned. I think we have them programmed at about a 270-degree field, orchestrated opposite of each other. And so it basically just creates a zone around the robot and the CNC where you can enter inside of. And then if I jump forward, you can see it a little bit with this bottom left. They didn't really label it. But the difference for color zones is you can set in the safety hardware, which I really liked, is you can actually set depth zones, and that's all up to, if you all want it one zone, you can set custom fields. But basically, the way we have it set out is we have a exterior field that is basically, everything's cool, robot runs at top speed. From inside there, we have it marked down on tape, so you'll see it when you get in the building too. There's a intermediate zone where the system detects you are present, immediately cuts the speed to 50%, but allows the robot to keep doing its job. Status lights will change in the cell, and then once you go on past that, that zone is what we determined as a, if the robot was reaching through here, there's a possible collision, so it just triggers a safety light e-stop, and then you have to re-enable. But if you don't trigger that last zone and you're just in that intermediate, you don't have to clear any errors. It'll just warn you it's running at a reduced but continue doing its job. If you hop out, it'll go back to full speed. And then that's the size scale. So these things are pretty small compared to older models. If you've seen like the LiDAR or light scanner systems on like much larger, older, you call them AMRs or AGVs, so autonomous mobile robots or automated guided vehicles, basically large warehouse things. This is their new tiny model. And then this is more of a, I don't know how much you guys do aluminum extrusion assembly. If you are a fan of an 80/20 like this is produced by Robo Units and then distributed by Olympus Controls. If you've messed with 80/20, I have a small kit with me I can try and demo. This stuff's amazing. So I worked between high school, college, everything else. I've had plenty of robots constructed at 80/20 or I have prototypes at 80/20. If it's only ever going to sit on a desk, you're probably not too worried about stuff torquing and twisting, but as you know, that you have to, with 80/20, you have to designate where all your holes are going to be. You're going to have to drill through it, either secure it from the other end or tap those holes. If the second you need to adjust something, yes, the extrusion is modular, but not the holes you tapped. So you have to retap. But then if you go and say we ship it around or it carries around, inevitably those beams will start to torque and twist, and you'll see everything get warped or kind of out of place. If I can make the mouse do the thing. So this here just, they have pieces that just sit in the slots. And so you don't actually have to, one, tap it. So if you want to ever adjust it, you just back off a little bit from the screw and you can just immediately slide back and forth. And so our construction has no holes that were tapped. But then that U piece actually goes in the end slot of the 80/20 and it prevents rotation. And so both themselves and ourselves, we've had stuff shipped and nothing ever needed to be tightened and nothing ever twisted out of location. Everything, once it's fixed, it's just absolutely in that position. And probably the next level after that, if you want to go really crazy, would be Loctite. But we've not had any torquing happen. So anyway, so as someone who's messed with 80/20 and had to nearly reassemble everything after they uncrate it, this was a godsend. All right, so then we get to task one of the projects. So task one was basically just figuring out what the system needed to be, and the first thing identified was what kind of materials did they want to pick up. So it's a CNC lathe, so they identified some possible different raw stock and what those parameters would be for that demo. What you will see is the middle image is the one that we landed on for the demo today. I'll go into more detail later. The original version of this was going to demo all three, which is why that dynamic cylindrical gripper was chosen, is so that it doesn't need to know the diameter of the raw stock. It'll just go until it senses it and grabs it. The hurdle we ran into was not the robot, but the CNC and the chucks we have that support that only have about a 1/4 inch of travel, unless you have to take them out and completely manually retune them. And so it doesn't really show off great to an automated cell if an operator has to constantly go in and readjust the chuck. And then, so this was the grip test. So this is me just showing off the different 3 diameters that were featured. And this was basically the early on question of, okay, the hand says it can grab it. Do we know for sure it can? And those rubber grippers you can actually take off. So I have more photos both with and without. But it was basically trying to figure out, what's the normal force? What's the friction? Am I going to drop a 10-pound part on someone's foot as it tries to not just go from overhead, but as I rotate it, as I shake it, is there a risk of slip? And the videos and photos, thankfully, everything stayed well in place. So then getting into task 2. Task 2 is basically like the assembly or the construction of the cell. That's where just going through down again, as you can see here, this is everything kind of put together. So we have the collaborative arm, we have the cylindrical gripper attached. It's cropped out, but I will show you in person if there's not another photo later. But down here is one of the scanners. The other one, I think technically is right there, but you can't see it from this vantage point. And then the extrusion fasteners, as discussed before. And then, yeah, go ahead. If anyone else wants to copy, and I can follow up with you guys afterwards as well. And then, so then this is to the Flexxbotics side. So in addition to the software and whatnot they provide, so if you've programmed it all within the UR ecosystem, they have these libraries that they call UR caps, and they're basically feature and software extensions that you can basically plug in. To me, it feels like downloading an app from an app store. So it adds features within. So if you go on this left side here, if I can make the mouse, maybe I'll just point. So if you go over here, this is like your regular programming interface. And so with the UR caps or your apps, this will basically add in a bunch of new features. But what it also does, as shown in the top right of the image, and it's highlighting Flexxbotics right now, is when you add these new features, you also get a quick click menu that then immediately provides on-the-fly operations that you can control. So by having the Flex system in, Those red dots are basically mimicking those like green ports you saw earlier. So it immediately provided buttons for the door, the chuck, the cycle start. And so if you wanted to just manually toggle I/O outside of the program, this comes back out. Another feature I'll go into more detail later, but was really slick for the programming, is you can program as a hard set, like what length of stock you're loading. But going back to the fact that this is a robot with safety features that it can sense when a collision is made, you can actually use that as a sensor. So what we did in this case is spin the fingers all the way closed, use that as a touch point, and then purposely collide into the raw stock. And then once that happens, it updates the program based on the height collision. This is the length of my stock. I know how far to insert it into the chuck. So there's actually no hard programming in the program. All the length and whatnot are left as dynamic, and so the sensing is able to update it. You, of course, if you're only going to one-run part, you want to get really concrete, you can hard set it. We just wanted to show the flexibility of it.
The nano scanner do.
What about the nano scan?
The scanner do.
Yeah, it's present. Oh yeah, it's way more invisible.
Repeat the question.
Yeah, what you're asking about what the nanoscan does? Yeah, so the nanoscan's that's the safety zone area. So if I can try to get the cursor to pop up, maybe. So here we have one featured right here, and then the other one, the top. If you kind of see these bars over here, and so that's that about 270-degree span. So we have it detecting on one side of the robot, and then the other one is kind of shooting out into the bay. That way no one can like sneak up behind the robot and kind of enter in where a collision might occur. And we actually had to, the scanner was sensitive enough, we actually had to tune it down, especially that one shooting out to the back into the open bay, because we found out that as the auto door opens, it triggers just back far enough that the safety scanner detects the auto door as like a human entering the zone and would just stop out the robot. And so we kind of had to add like a blind spot to allow the CNC door to operate.
If you were to lay that stock on the table sideways, would it adjust and pick it up differently, or?
Not in the current config, because right now the question was, if I laid the stock down sideways, would the robot be able to turn and still pick it up? Mechanically speaking, the robot can do that. Software-wise, the robot would not be able to compensate for that in the current config because there's no vision on the system. So there's no sort of sensor or I/O feeding back into the robot that a change has been made. So I'm using the force sensing to dynamically update the diameters, but the orientation is currently a fixed system. I would need vision or, yeah, vision's about the only thing that comes to mind right now to try and make that update.
They have systems like that?
Oh yeah, oh vision, we don't feature vision in this one. I could ramble to you a bit about vision. There's a new startup in Eugene that has made that crazy simple. So instead of the old school of, knowing your C libraries and trying to, or like I have a Cognex camera out there right now, and so it'll do like 2D matching, and then you kind of have your like AI based on that, so it can kind of pattern recognize. But there's a small startup that I want to get my hands on out of Eugene, Oregon, where they've implemented block programming to their vision systems. And so instead of needing to understand the old school approach to programming, it just has these color-coded blocks of, do you want to detect an object? Is that object closest to a circle, rectangular, triangle, whatnot? And then the next block is like, okay, if case, wait, and then what like tool or operation do you want to perform? And so kind of how I was describing how I was able to teach high schoolers on the fly, they kind of have demos where they're like, okay, someone hasn't messed with vision before, here's this new setup, we have them going in like 10 minutes. And so that's a thing I would like to get my hands on and then feature here at some point, because the barrier to entry for that vision system was really nice. Yeah.
So in this setup that you did, the operator has to feed the raw stock into a certain location for the robot to detect it, to feed it to the machine?
Yeah, so the question was, in the current setup, that the robot would have to basically prep the part presentation tray. And yes, in that case, that's what's being featured here. That was basically just to limit the scope of the cell. What it's supposed to be mimicking is, say, if you had like a parkable part tray, and then the tape is basically like what the indexes were. So as long as you had something that was consistent, then the robot would know where that is. If it was less consistent, you could either add a vision system, or another solution, if you guys haven't seen before, is maybe you have a part tray, but you don't have some sort of mechanical apparatus where it parks, so it's always locked in the same position. In that case, there are multiple solutions that exist. I think Flexxbotics featuring one, where you can either scan a QR code or do a mechanical touch-off, and then immediately update like the coordinate system relative to the part presentation. Any other questions before I move on? Okay, so then the advantages. So in this case, discussing from an automation standpoint, right? So we were able to operate the door, the chuck, load programs, call out the cycle start and end. Through this whole time with the Flexxbotics system, we're able to be monitoring for alerts, changeover analytics, on and on. One of the big key proponents for why this even launched off is, like I said earlier, the ergonomics of it. So having people try to, with a single arm, reach out 30, 40 pounds, historically, their data shows that was terrible for the operators. And then the collaborative portion, which is, no cage was needed. We had the safety light scanners and the collaborative feature of the robot arm. You will also see, I didn't mention it here, but going back to the ergonomics, so there was some finesse to get them both to coexist, because if the operator is going to exist within its normal point to operate the CNC, that's also exactly where you would mount the robot. So this one is offset so that the operator is uninterrupted, but if you are to translate the base off to the side, you imagine then where the joints of the robot are, it doesn't exactly line up with the door. So there was some finesse to getting the angle and positioning right, that the elbow is actually to clear through, and you'll see that when we go on the floor. And then just in conclusion, so this is a full view. This actually touches a little bit on what I said. So the robot is offset, and then if you look at like that square tray at the base of the robot, it's also offset. So that gave it the right angle so that the joints would clear the door, since it is no longer directly in front of the where the auto door opens. And so basically operators and robot was able to coexist and collectively complete tasks. Automation on a high level is accelerating, going back to the trauma I've had in the past, splitting and pull testing hundreds of wires, to now see all the tasks I've done in the past be simplified by a single Ethernet connection. I am both grateful, and then think about all the pain I experienced in the past that led to this. And then the safety scanners that were featured operating as dynamic zones, so you no longer have to have light curtains or other scanners, where it's just the second it detects anything nearby, it locks out the system, but you can actually both warn the operators, you can flash to identify the area around it, and then you just slow down the robot. It doesn't immediately mean any stop, it stops everything, and then someone has to go and reset. And then just back to the software in terms of, you get into a tight place, and Flexxbotics was able to help manage through, like, oh yeah, we saw the errors that were flagged. I think there was at least 2 cases where either via cell phone or Teams, they reached out to me and they're like, hey, are you testing the robot? We saw something go weird happen. And I'm like, conveniently you called before I called you. Yes, how can we fix this? And then, so next steps. So in terms of evolution, what stuck out to me, a few things that if this project was to evolve, continue, explore more for the customer. One of the things I would like to do is go back to showing that the robot and gripper can actually handle multiple diameters instead of what we just featured today. And that goes back to needing a chuck jaw that can travel more than 1/4 inch and actually adapt to those things, right? The CNC obviously has to be able to handle various raw stock without mechanical operator intervention. Another thing that you'll see out there, it works, but would probably switch out from the 3-finger cylindrical into something more like just a 2-finger gripper with like V-chucks to grab the cylinder, something like that. Reason being for that is once we completed the demo, it was identified afterwards that the customer's like, oh, well, we really wanted to see both faces like get exposed to the cutting tool. I'm like, oh, I didn't prepare for rotation because I'm grabbing the end of the raw stock. So now I have to grab the end and kind of like performa. And so there's an intermediate step with a V-block that's basically mounted to the part presentation tray. But if you were instead of grabbing the face of the stock, if you just grabbed in the center, you could just grab it, flip it directly into the chuck. Obviously, that's going to be a lot more streamlined of a process. And then the other things I have featured here in the photos are testing out different new safety equipment. So the top one is a safety radar that they have. And so that is able to put out a 3-dimensional field. And that one, I've seen one demo of it. I need to play with it more. That one, they say that they've beat on it and sprayed paint on it, and the radar still works unhindered. And so that would be something interesting to test, because the radar is going to be less susceptible than the light vision systems for casting zones. And then the bottom one is an interesting new feature that I've seen. I think they're still working on the firmware. It's out, but I've seen some interesting implementations. So it's that bottom right photo. It's a vision system that casts a safe cube, essentially. But what you need to be careful about in the implementation is that you need the scanner to be aware that the robot's going to move, because if you tie a cube over motion and then it detects the robot or CNC moving, you've now caused a lockout to your own cell, and then you have to either override the safety or remove the safety to then be able to allow the robot to move again. So be aware of those conflicting interlocks. That was something we raised during the implementation. We're like, well, what if the things that are supposed to move do move? And hey, we got a quiet response. And then context. So any of the hardware, software products featured today, these are the individuals involved and how you might get a hold of them. And I can hand out that information as well afterwards. And the contacts might be the last slide. Yeah. So with that said, any questions?
Actually, I'm going to hand you a mic. We're currently live streaming right now, so just to make sure it's picked up.
Does the robot have the ability to automatically change the end effectors if you have multiple?
That's more of a, the robot arm itself, no, that usually defaults into like, so whoever built that hand is the one who then builds the tool change system. So that exists, just not on the cell, because I just have that one hand. Oh yeah, so automated tool changing is a thing, and they have a few different ways to do it. So there's, I'm trying to think off the top of my head, there's a few companies that have done like an air interlock. There's a mechanical interlock where it'll kind of like cinch in and grab a hold. And then there's another company that, I have a prototype, but I don't have it mounted. It's almost like a spring one. It's kind of interesting to watch. So you have to bolt the receiver onto the table, and then basically what you do is there's a push pin that comes around the wrist, and you basically just slam the wrist in full speed, pops the lockout, catches the hand, and then you just go and grab the next one. But in terms of switching without like an operator needing to do it, yes, they exist. Yes.
Is there a weight limit to or what's the heaviest weight these collaborative arms can lift up?
So the one we have today, the UR20, will be a 20 kilogram load, so roughly 44 pounds. We're not going to push the 44 pounds today, but that's the top for that brand, UR. Last I've heard, but I don't remember if it's in production. I think Fanuc already has a 25 kilogram model. I don't believe they've released yet their 35 kilogram model. And then you kind of end up chasing details once you start getting into those heavier payloads. Because I know in the past, other manufacturers that had a heavier Cobot, it wasn't a true Cobot. What they did is they just put like a 2-axis or a 3-axis force sensor on the base of what's essentially an industrial arm. And so it can't really measure collisions as good. It can just, if the base flexes, but that's not the same as the wrist flexing. And then it also doesn't come with the software to let off of a pinch point. UR, I think, is coming out with it's a 25 or 30 kilogram model. But Yeah, and that's the one where it's stockier. So there's an iteration where when because people will obviously ask for higher payloads, that gives you more options to work. So usually the first iterations when you see a company release a higher one is they actually step the reach back, so they just make all the arms stockier, so just thicker diameter and shorter, and that reduced reach will help them with the heavier payloads. And then it's usually a generation after that you see more reach with higher weight. The other thing that happened I think the conference was in Florida, but I'm blanking on the name, Tyler, you might be aware, is so these collaborative robots are safe, certain safety features are removed, they can detect collisions. A 40-pound part still has inertia, and colliding with someone, whether or not you stop it or not, it still doesn't feel great, especially where it hits you. And the taller the robot, the more likelihood it can hit something above the waist. So one of the most recent conferences was discussing, hey, as we try to pursue 30, 40 plus kilograms, we're getting into heavier and heavier objects with more and more reach. Is this still considered collaborative and safe? Because now the momentum and the size of it can do serious damage even if it detects a collision. So that's something that the industry itself and collaborative has to figure out and evolve. Any other questions? Yes.
Can the robot be flipped upside down?
Yeah, I can repeat that. Yeah, so basically you're asking like, other orientations, right? And the answer is yes. And I went through a training. A lot of these robot distributors, they'll have like a week-long intensive course. So I actually did a 4-day training at Olympus not long ago. And in there they talk about how mechanically you can put it in any orientation. Programmatically, you will screw with the coordinate system, because if it thinks it's right side up, its gravity compensation is going to be off. So one of the reasons you can teach the robot, where you can just drag it like a stylus, and when you do that, it's called free drive mode, or I call it like anti-gravity mode. It's basically you release all the brakes, but it doesn't fall to the ground. It's using the force sensing in all the joints to basically float in free space, and that's how you're able to quickly go around and touch it. If the robot thinks it's right side up, you mount it upside down, and then you release the brakes, it's going to freak out. Now, that being said, there's just an installation menu that you just say, what is the orientation of my robot? And they even have pre-existing templates. I think 2 of the most common templates are the inverse or a 45 offset. And so once you say that, it'll update the coordinate systems, but more importantly, it'll update the robot on what it thinks its gravity should be when the brakes are released. Yeah, I would think in a more streamlined process, we don't have, as you go out there, we don't have the structure to support an upside down, but as you saw with that auto door, I would say, especially in this use case, an upside down mounting would make more sense. It's more out of the way, cleans up the floor.
We see some on the machine itself too. You actually have the robot mounted to the machine and then doing the inside.
I'm just thinking trying to clean up the floor space.
Yeah, no, absolutely. It's just not something we structurally had accessible, but I do prefer that mounting solution. Any other questions? All right, well, with that, I think we'll start the tour then.
Perfect. Well, actually, we're going to have another presentation.
Oh,
just
my
want to
bad.
say thank you, Jordan. And just
Jumped the gun.
so you all are clear, we did get clearance. More than happy to share these slides after this presentation. So we'll be able to post that online to give you guys a chance to download and see it for yourself. If you have any additional questions, please feel free to reach out after today's event. I'm more than happy to make those connections. So with that, if you can give us 5 minutes, we're going to get Tyler Bouchard to give his slides. So awesome. Thank you.
Nice job. Okay, that's great. Yeah, go ahead. Perfect. Let me just make sure everything works like it did last time.
Would you mind just saying a couple things?
Test.
Okay.
Audio, good?
Thank you.
Okay. And then what did we do?
We had to.
You did that one.
Yeah, hit that bottom section, and you have to choose which screen you'd like to show.
Let me do this first. That. And then if you do that again. yeah, so if we do that, then what I'll do is I can, if you click that, do this, I do that,
There we go. Gotcha.
and then do this. I think it should be nice. Yep, and we're all good. Let me know when I'm good to go.
I think we're good whenever you're ready.
Okay. All right. Thanks everybody for joining. So I'll give a quick introduction about myself. So my name's Tyler Bouchard. I'm CEO and co-founder of Flexxbotics. So I started my career off in engineering, same as Jordan. I actually went to a school in the Northeast called WPI, small engineering school. And then I started, my kind of industrial career in working for companies like Cognex, Mitsubishi Electric, Novanta. So pretty much my whole career has been within factory automation or providing motion control components for factory automation solutions. So I've been robotics and manufacturing pretty much the entirety of my career. So started doing my MBA at Northeastern and got through doing that part-time. About halfway through that, dropped out of that to start Flexxbotics with the other co-founder, who's also named Tyler. His name's Tyler Medelsky. He'll be doing a presentation later today to kind of go into depth more of application that we've done. So we started that company. So we started Flexxbotics about 6 years ago, and we focus on advanced robotic machine tending. So since that inception, we've accrued about 177 customers within medical, aerospace, automotive, and defense applications, and providing advanced machine tending solutions for them. So today I'm going to talk about robot-driven manufacturing with autonomous process control and how you can be able to scale robotic automation within your manufacturing environments. First, I'll start off with a quick little video. Great. So that kind of gave a good overview of some of the things that we focus on. But jumping in now to kind of some more of the details. So I like to start off with this slide, and basically, as Jordan was talking about, there's a lot of complexities that come with robot automation. So robot automation is hard, and if anybody tries to sell you differently, they're wrong. There's a lot of things that you need to take into consideration. So, I think from our experience, a lot of times, walking into manufacturing facilities, pre-Flexxbotics and, while with Flexxbotics, there's been so many times, come in and seen a robot that's not running and have asked, hey, what's going on with that robot? Why isn't that robot running? And, there's a whole host of reasons of why that happens, but, effectively, those robots are acting as expensive coat racks because of projects that have failed. So, what we found, communicating and talking with those customers, is that most robot smart factory initiatives break down at the work cell level. So actually implementing the robot into the work cell and into your process to be able to run everything. So the main reasons that we see with that is, the first thing, like I was talking about, underestimating the complexity that comes in with a robotic application, either from purchasing the robot or from somebody selling the robot to say, hey, everything's plug and play, it's going to be easy, get everything up and running, and there's a lot of other considerations that need to come into it. Another thing is the equipment, which Jordan was talking about before, can be is incompatible. There's a host of other industrial protocols that robots and machine equipment have, and inspection equipment, and having them all communicate and coordinate with each other is something that a lot of technology is lacking within robot automation. And then the final thing is we see a lack of process integration into the robot. And so process integration into how does the robot interact with the equipment, with your people, with your IT systems, upstream, downstream processes. While it's contained within that individual work cell, its reach is beyond that, and being able to integrate it directly into your process is something that maximizes the performance out of the robot. So we like to kind of be able to, orientate individuals on what is the robot automation journey. What does it look like? What are the steps and processes that need to come in place for you to be able to effectively scale automation? So first one we start with is, conventional factory machining. This is moving from, manual machining to automated machining, which, you go into any machine shop now, that's where a majority of the machines that they have are automated machining setups that they have. Moving from, the historical Bridgeports of the past to now having, of course, something with a size like a 5-axis DMG Mori that I think can hold, 3,000 to 4,000 tools inside of it. So a lot of the technology within machining has advanced. What we're seeing now within the second step is what we call traditional robot machine tending, which is basically going from having the manual tending of these machines, these automated machines, to now automating these automated machines. So you have actually robots standing in front, that everything that Jordan was talking about in that application, and having that robot be able to tend to that machine. So we're seeing that a lot of manufacturers are starting to get their feet wet in implementing one or two of these robots in this, and understanding how that process works. When we get into looking at how to truly scale robot automation within your manufacturing facility, you start to get into some more advanced aspects that allow you to be able to go from those 1 to 2 deployments to how do I automate 70% of the machines within my facility, 70, 80%. And so that's when we get into the next steps, which is robotic process enablement and autonomous process control. So starting with robotic process enablement. So this is the ability when we think about how does the robot interact in the work cell and the immediate interaction of people and business systems within that work cell. So having the ability for the robot to be able to communicate to everything within the cell, coordinate everything in the cell, and then the individuals that are interacting with the cell on a daily basis. How are you, supporting the cell? How are you configuring job setup? How are you, troubleshooting issues that are happening within the cell? So, truly integrating that robot into your process so that you can be able to make sure that it has maximized performance within there. The next one is autonomous process control. And so this is when you're incorporating inline inspection, or if it's the last portion of your process, end-line inspection, and more advanced aspects of your IT systems into the work cell and robot to be able to create basically closed feedback loops. So you're driving basically information to the robot from, say, the output of your inspection equipment, or for the configuration of a job through your IT systems, or specifications of your parts, everything that that a human operator or engineer would have at their fingertips within the cell to be able to see that everything is within specification, providing all that, providing that closed feedback loop, so that the robot has the power and intelligence to be able to run the cell autonomously. So it's providing basically aspects of statistical process control and autonomy with the robot to be able to truly get a lights out manufacturing setting. So you combine all these aspects, and this leads to what we view as robot-driven manufacturing, where you can be able to have fleets of robots across your manufacturing facility. But it's important that you have the building blocks of these to be able to achieve that, and it's not just buy 20, 30 robots and start deploying them. It's creating the infrastructure for you to be able to effectively scale that. So going through, there's a host of challenges along the way and each benefits at each of these stages. I'm not going to go through every single one of these, but you can imagine, some of the benefits that you have for integrating a robot into your process, utilizing inline inspection to make sure your parts are inspected every single time, running in a lights out, having increased capacity, highest utilization possible, aspects like that. But what I will focus on is where, what I was talking about before, where a majority of projects fail. So it's where you have your first or second robot, you can go and you can implement it and you can put it together and maybe you can piecemeal some things, to make it so that it's operating. But if you're looking to be able to scale to a point where, anybody within your facility can be able to operate these robots and you're able to increase the volume of robots that across your manufacturing floor, we see that a lot of initiatives fail. We look at it kind of the robot chasm from traditional robot machine tending to that robot-driven manufacturing. So the reasons that we see these projects fail with some of the problems that I was talking about before, everything is disconnected. The robot's not directly communicating with everything within the cell. Thinking about the process integration, thinking about what parts are going to be running, thinking about optimized mechanical setups to make sure that you can be able to handle changeover. If demand changes with different parts, how can you switch out other parts to make sure that the life cycle of that robot has the highest utilization possible. So the next thing kind of to look at too is, how does the robot fit into the current manufacturing technology stack? So anybody's familiar, with the basic manufacturing technology stack, it starts at, your sensors, which leads up to your PLCs. Then you have your SCADA systems, basically data acquisition and visualization, as well as your HMI, which is your human-machine interface. So how do you be able to configure and operate the cell? Up to MES, manufacturing execution software, to your ERP, enterprise resource planning. So this was a question that when Tyler and I, before we founded the company, and something that we do today is think about how does the robot fit into the manufacturing technology stack. Looking at before previous solutions were not built for the robot; they were built for human operators, and so those business systems operate in that capacity. But it doesn't take into consideration the robot and how that fits into there. So starting at, basically we said, okay, where do we want to be able to start at and to be able to start integrating into the manufacturing technology stack? And so we started first at level 1, which is the PLC. And Jordan, I think, did a really good job explaining some of the complexities that are around that. There's a whole variety of industrial protocols that manufacturing technology utilizes. And when you get into machining environments, as you guys know, working in your machining environments, there is even more variety in the controllers and protocols that are running on there. So you can see that there's a full list, and there's multiple, even more that are out there. So it can be overwhelming when looking at, I have robot, be able to communicate with my machine, with my inspection equipment, with my business system. How do I be able to set that up? And something that we see too is you might have a machine that's the same model for their controller, same model of the machine, and identical, and you'll have 2 different configurations on that controller. So the variety doesn't just limit to the actual providers of the technology. It's actually something with when that machine is manufactured, it's has its own independent configuration. So there's a lot of variety that's around that. So we started working effectively on a way to be able to have essentially a bilateral communication between the robot and those PLCs that are operating within the cell, whatever equipment that it's using. It's important that the bilateral aspect of it, we're not just pulling information off of the machines, we're actually pushing information onto the machines, and we're pulling it to the robot and pushing it from the robot onto the machine. So that bilateral communication allows you to incorporate things like safety, better control of what's going on, be able to have better context information that's happening, be able to have more advanced logic between your robot. Since we did that bilateral communication, we had basically the base level of communication between all of the equipment. So we further use that contextualization of that information to be able to, be able to do further integration to business systems, to be able to say, what's the state of my machine, how to be able to, upload and download programs from your machine, from your robot, and be able to have, effectively complete control of the work cell through the robot.
Do you have an example to integrate with MES? For example, the robot is some parts run out, and robot will wait for the supply to new parts and it start running. Does it have an example that you can integrate or talk to the MES?
Yeah, definitely. From the question is example of an integration into an MES platform. So we have within our software, Tyler Medelsky, he's going to go do a full demonstration of the software and apply it to applications. And so he'll show you exactly the software. But we have a job manager, which basically is looking at the parts that you're running within there and then applying it to essentially to the robot cell. So it has your robot program, your machining program, and all the other information that you have. So we can do an integration from that, pulling that from your MES to be able to help that deploy it into the job. And then because we're providing contextualized information of everything that's happening within the cell, we can feed that back up into the MES. So you can understand how many parts did I make, how many were within spec, how much is within WIP in this cell. It's going to the next cell. The average cycle time for that cell, what's that going to be? So we can feed that information. So we have our own where it's kind of our own standalone where you can be able to utilize that. Or if you have your own MES, you can be able to take that information and basically pump that in there. Does that help? Cool. So that resulted in our technology, which we call FlexCore. So FlexCore is a low-code environment to build and manage high-performance connectors between robot and machines and your IT systems. So these connectors, like I said, they're bilateral connectors, so they directly communicate and coordinate all of the manufacturing equipment that's within the cell. And it creates that closed feedback loop that I was talking about. So those closed feedback loops can allow you to be able to make programmatic changes in real time happening. So based on you're within this state, this is the output of your inspection equipment. Be able to take that information and actually be able to change something on the machine in real time to make sure that you're doing that configuration, which is exactly how when a human operator is within the machine, things are happening. They're getting feedback of what's going on, and they're changing things on the machine in real time to make sure that that next part that comes out or that current part reworking it is going to be within spec. So we've built hundreds of these connectors, which has allowed us to make our technology compatible with thousands of machines and different variation of machines and equipment that are out there, effectively making our technology agnostic. But there are situations where we do need to build a new connector. And what's great about our technology is that we can be able to on-site create a connector in usually less than 2 weeks and in most times less than 1 week, which in a custom integration could take several weeks, months, and a lot of times we've seen where it's not even possible for some of the things that, the way that we're doing our communication and the functionality that's being able to provide. So the answer is always, can I communicate with, can Flexxbotics communicate with this machine or this equipment? The answer is yes, we already have it, or if you give us, 2 weeks or less, we'll have something built for you that you can be able to have running in production.
So if you build a connector, the hardware part, how about the software part to read from the connector? This also can be done in 2 weeks?
Yes, yeah. So the question was, when you're doing the connector, is it both hardware and software? The answer is yes. So we have, what Jordan showed that, and you'll see it out in the demo. We have a black box that basically has off-the-shelf hardware that's inside of it, but inside of that sits our FlexCore software. So when we're building a connector, we're using our API internally to create that connector, and then we create a new build of the software, we put it on, and then you have that a connector is available now within that library. There are some things that we're not going to show today, but can talk about. We're starting to externalize that API, so individuals can be able to start to be able to create their own connectors and sequences.
If I have a Cognex camera
Yes, exactly. So Cognex is one that we're compatible with already over TCP/IP, and then we communicate with that, and we can be able to use that. Basically, we have it depending on the robot manufacturer. Like we're talking about Universal Robots within Polyscope. Fanuc also has their software where it's specific nodes that are in there, that nodes that we have that can be able to communicate with that equipment. So it embeds directly into the robot software as well. Good questions, yeah.
What about legacy? What it would be kind of our machines, legacy machines?
Yep.
Old models. Is this integrating with those machines? And second question is this require changes to G-code for outputs for the system? Will there have to be G-code changes?
Yep. So first question is legacy. Does this communicate with legacy equipment? Second question is what do I need to change within my G-code to be able to create compatibility? For legacy, answer is yes. It's usually, depending on the age, it can be a limitation of functionality that you want to be able to provide. So for example, we can write offsets in real time to a machine. It's not a hard cutoff date, but the technology seems around 2006, 2007 is when that functionality for a lot of machines falls off. Before that, and then after that, can be able to provide that. So it depends, and this is something that when we come into a project, we always say, what are your business outcomes, operational outcomes, whatnot, and then we can tell you the technical limitations that are going to help you achieve that. So, and there's certain ways around being able to get certain level of that functionality. But yeah, so that's a simple way. From G-code, there's generally no alterations that you need to make to your G-code. We are communicating directly with G-code, and we can upload and download G-code from the cell. Sometimes there are certain things where you're maybe applying like an M code to be able to operate a peripheral, like the door inside of it or your chuck, that you're putting in your program that you put in there to be able to fire off, to be able to inject that into the full logic of the program. So there might be something where you're utilizing an M code that you haven't historically in the past utilized, and where you're doing that. But all of that stuff is, majority of that within our software, you can configure it to be able to do those G-code uploads, M codes, or write offsets in the logic, and then be able to inject it depending on what you're doing within the program. Cool. So I've been talking about the functionality throughout, but this is just to kind of go over, in more detail some of the capabilities that we have. So starting off with some of the basic things, right? Being able to do a cycle start, detect when a cycle has ended, be able to do peripheral I/O control. This is something that part of for any initial automation project that you're going to do, these are going to be some of the basic things that you need to be able to have to be able to initiate between the robot and the machine itself. Some of the more capabilities that we provide, since we have that direct communication that's happening between everything, we can take and have real-time data monitoring. And we use that real-time data monitoring in multiple aspects. You can use it to be able to have information on part count. We can have failure count. You can have states of the machine. You can have basically alerts, escalations that can be used. So this is when we talk about process integration, making sure that the robot is interacting with actually the people that are running the robots. This is where you can be able to have that greater integration to be able to get highest utilization out of your robot. Then third one is I was talking about for program distribution, familiar with DNC type of functionality. This is like a DNC Lite functionality that we have, the ability to be able to do rev control on your G-code programs and then be able to upload and download them. I know for some customers, there's sensitive applications where the machine needs to be purged after every job that's being run on it. We have that ability to be able to do that. So we also have the ability to do historical analytics of what's going on within the cell. We use this to basically, we start off a project, what's our target ROI, what are our target metrics that we want to be able to do, so we help the customer be able to match those targets and be able to see how we're trending towards that. But we also use the analytics to be able to actually see, and Jordan touched on this, is the state of everything within the cell. So where the machine state was, what was the prior states of the machine, what was the prior states of the robot, and be able to then troubleshoot and get to root cause on issues much quicker because we have access to all that information. And you can understand trends of, hey, this issue happens. Every time we have this issue, it's because of all these states. This is probably related upstream to something that's, bringing the part in and out of spec, or, could be a whole host of things that it is. But this allows you to be able to have visibility into that. And then the final is the ability to take inline inspection. This is the autonomous process control we were talking about. So you can be able to take inline inspection, the output of that, and be able to update things in real time on the machine and robot based on the output of that inspection equipment. So I will go and talk a little bit more about utilizing inline inspection. I talked about there's inline inspection and then being able to have, if it's end-line inspection into a cellularized setup. But we specialize with incorporating inline inspection, and inline inspection can be anything from utilizing a probe within your cell to having a full CMM in the work cell, depending on what do you need for the actual inspection criteria, and then what is the operational outcome that you want to be able to do. Are we just trying to reduce capacity at our current CMM so we can be able to look at some key areas? Or do we want to have something inspected entirely so that when it gets inspected, it's actually ready to be able to ship out the door? So understanding that is, how kind of the selection process. But with our, compatibility, we can be able to utilize any of these types of inspection equipment to be able to incorporate it into the cell. So I've talked about, the combination of statistical process control and your robot, and having a kind of autonomous function. So we have that within our software. We can basically be able to do things like, take with your part specifications, set tolerance thresholds. We can be able to provide some light statistical process control type of functionality of when do you want to be able to apply an offset. When should we apply an offset? How often should we be applying an offset? Should we even apply an offset? And then other information of being able to see how your parts are being manufactured in accordance to your specification. So this is really the strongest level of feedback that you can get within an automated cell, which is something that, you think about, put a robot in, you don't have that feedback system anymore that the human normally has. Putting in inline inspection really allows you to be able to have the best visibility possible to make sure you get the highest level of performance and output of the robot, that parts that are within that specification. So just wrapping up a little bit. So what happens when you standardize effectively your implementation and the implementation and operation of your robot is you're effectively able to scale both horizontally and vertically your robot automation within your manufacturing facility. So by horizontal, we mean from application to application. So if you have a standardized interface, a standardized implementation, standardized human and machine interface of how you're operating within the cell, all those things allows you to move from either, if you have a set of applications, you can quickly be able to integrate the robots into those applications. And if you transfer over to another application, you're still doing it in a similar fashion with how you're doing the communication, how you're doing the operation. So it allows you to be able to horizontally integrate. And then because the vertical integration, which is basically integrating the robot into your manufacturing technology stack, you're basically allowing yourself to be able to create more autonomy with your robot because you're providing more information into it. So to summarize, the combination of these approaches, in our eyes, looks at providing the most productive, robotic setup as possible. So, combining them together, you're able to run unattended longer, continuously, and everything within spec, leading to the best throughput possible. And then a really important aspect is an increased profit per part. So it's the old adage of doing doing more with less. So I think that summarizes the presentation, but open up for questions. Yeah.
Yeah, I have one more question. What is your ability to integrate with maybe like a competitor's robotics platform, like a FASTM system?
What kind of system is it?
Like FASTMs?
Sure.
Like you're maybe not the robotics side, but the MES reporting side. Like integrate their information into one solution.
Yep. Yeah. No. That's so. The question is, is I'll kind of summarize the question maybe a little bit different way. Is does Flexxbotics solution compete with some of the existing business systems that are out there? Like FASTM's MES. And the short answer is no. We work in conjunction with those business systems. There's a lot of functionality within those business systems that we're not doing. Everything that we're doing is focused on the robot. Everything is centralized around the robot and is contextualizing information about there. So if you don't have an MES, you can use it in some MES functionality. But if you already have an MES, there's a point where you want to be able to have an integration into the MES and be able to push and pull information from there. So we do it in both ways, depending on what are the existing business systems that are already in place. Same thing with ERP systems.
Do you also provide solution? For example, my question is, do you also provide a solution, like a service for solution? For example, if we have a robot, it doesn't have a integration solution, could you come and then provide a solution? For example, create a connector, create an interface, and then provide some customized software to enable this robot to connect to the MES or even though we are not using your robots, but probably we are using your solution. Would that your company be willing to do?
Yeah. So the question is, do we have additional services outside of our software offerings? And swear to God, this is not a plug. You didn't plug this question. We do provide actually turnkey services for customers. So everything from mechanical design. So we can provide a full turnkey cell that has mechanical design of your gripper, your in-feed, your out-feed. Depending on, a lot of times customers take on their own work holding inside of the machine, but we can help with the design of that work holding, and then provide all the communication aspect and then business system integration. So we do projects for customers on a single cell, and then we can do multi-cells where you're doing a full kind of like technology implementation of robotics across your manufacturing facility. So this is something that we provide and can do on a project basis. Yep.
So are you effectively an integrator then, or?
So the question is, are we an integrator? At the heart, we started the company and still to this day have a lot of resources that within software, but equally we have integration services that we do provide. So the best way to describe this is we're hybrid. Software solutions, but at the end of the day, software doesn't really work unless you're actually implementing it in the real world. So our implementation services help kind of bridge that gap for customers.
So if say for instance, we were installing a cell into one of our plants and we asked you guys to take part in that, would you be working with another integrator or integration company, or would you be the company putting everything together?
Yeah, so we can do it both ways, depending on the level of scale of integration. In most cases, we are the lead integrator in that sense. So we take responsibility of the entirety of the project. I think Jordan was talking about safety. So we do part of our services. We provide a full safety risk assessment. I forget the ISO standard off the top of my head, but we provide that safety risk assessment and can provide all the information. So we're taking full responsibility of the project from design, implementation, and then we do full support the life cycle of the robot. So we're providing that ability to remote support, troubleshoot. We have weekly reports with, we work back and forth on potential optimizations that we can make, because at the end of the day, a lot of what we see is hardware gets put onto our customer's doorstep and goes, all right, it's yours, good luck with it. We take a completely different approach where we're with you essentially as kind of a automation engineer, manufacturing engineer on call to help make sure that cell's running, and then that cell is always performing at the level that at the beginning of the project that we set out to say to be able to achieve that ROI and operational effects that we want to have to be able to effectively match that. Yep. Yeah.
What kind of programming languages do your robots typically run on?
So we, from a compatibility standpoint, we work with a multitude of robot providers. So Universal Robots, we're compatible with FANUC as well, Epson robots. So we use their native programming languages to be able to communicate directly with them. It's the same example as in with machining controllers in their programming language. We're operating within their native programming languages. So what we have is our in-between programming language that we then do as a translation between both of them. And then we have, when it comes on the robot side, we have basically the URCAP for Universal Robots is basically a plugin. So we have our own Flexxbotics nodes that work in conjunction with the native, what Universal Robots' programming language, Polyscope nodes, work directly in unison. And so that helps basically create your programs and then create that communication translation over to the machine as well. Yep. Yeah.
Do you guys deal with situations where, like both situations where somebody comes to you and says, I have this issue and I want to come up with some form of solution with robotics? And also do you deal with situations where they're like, hey, we've got this robot and I know how I wanted to implement it, but we can't do it. And then do you kind of help step in and kind of help build that? Do you guys have both situations?
Yes, both. The second one we call those rescues, where a robot's been deployed and it's not operating to the way that customer wants, for whatever reason. We come in and we can help provide, basically a way to, get that robot back into production and operating maybe in a entirely new capacity or in the capacity that it was intended for originally. I think your first question was around coming up with a new, say, design for an implementation. So yeah, we look at it as like a collaboration. Right? So you have, effectively what you have on your side that you're looking for, hey, we want to be able to achieve these certain types of things. And then on our side, we have a bunch of expertise in implementing automation in machining environments. So we like to combine that combination and be able to consult on what is the most productive solution possible. Taking into consideration everything around, well, why are you integrating, automation in general? Like what's the initiative? What's driving that initiative? Down to, hey, here's the technical detail of how we're going to flow air through here so that it doesn't interfere, right down to that level. Yep.
The software is called a Polyscope.
Yep.
So is that industrial, like a standard software? Is unique to Flexxbotics?
So that is Universal Robots software is Polyscope. So it's I wouldn't call it necessarily a standard industrial protocol, our standard, but it is their software programming that they utilize with ladder logic type of robot programming configurations. Yeah. So that's separate to us, but we have plugins that work with that directly.
Okay. Thank you, Tyler. We're going to take around a 15-20 minute break to set up the next call, which will be virtual. So feel free to grab some more coffee out in the foyer, use the facilities. We'll reconvene at about 10:50. So thank you very much.
Thanks, everybody.